I will be explaining you Tutte's theorem. So this is the statement of this theorem. G has a perfect matching if and only if number of odd components of G minus S will be less than or equal to number of vertices in S for all S subset of the vertex set V. So here this is an if and only if statement. If you want to understand what they are saying in this statement, you have to know first what is perfect matching. So if you want to know that, you can check out my graph theory playlist. There I have uploaded a video on perfect matching. Okay. After watching that video, you will be clear about what is called perfect matching. So here they are given you a graph G. That graph is a perfect matching. If and only if that graph is a perfect matching, then the odd components of G minus S. G minus S means what? From the graph you are subtracting sum of the vertices of capital V so that you will get the graph G minus S. So the odd components of G minus S is less than or equal to number of vertices of the set S. That is what you are going to prove. Or if this condition is there, then G will be the perfect matching. Or if G is a perfect matching, then this condition will be there. This is what the theorem. So here this is an if and only if statement. So what I am doing is, first I am assuming this, and by assuming this I will prove this. Okay. So that is what I am writing in the first two sentences. Assume G has a perfect matching M to prove number of odd components of G minus S less than or equal to number of vertices in S for all S subset of V. Now you are writing about what is that S. Okay, here S is that. Let S be a proper subset of capital V. You know that what is capital V? Capital V is the vertex set of the graph graph G. Okay. Now what you are doing is you are finding the graph of G minus S. Okay, you are drawing a graph of G minus S, and from that graph G minus S you are considering some of the odd components, and that odd components are G1, G2 etc. up to Gn. Let G1, G2 etc. up Gn be the odd components of G minus S. Now what you are doing is, here Gi is odd. It means in general they are writing here G1, G2 etc. up to Gn are odd components. So in general you are writing Gi. Okay, here Gi is odd. So this is odd, so that what will happen is, here you can see the odd components of G minus S. Here you can see the S subset of V, proper subset of V. S you can see here, right? So this is S set, and here you can see the odd components of G minus S. So here these are odd components. So some vertex Ui of Gi. Okay, there will be some vertex U1, U2 etc. up to Un. In general they are saying Ui of Gi. There is some vertex Ui of Gi. They are present in G1, G2 etc. Gn, right? So in general they are writing must be matched under M. They are alone, right? U1, U2 etc. This Un are alone. They are without any matches. So what will happen is, they will be matched under M. With whom they will be matched? They will be matched with the vertex Vi of S, with some vertex that present in the S. Okay, that is what you are writing. What is meant by matched under M? The meaning for what is the meaning for this matched under M? It means, okay, it means here you have consider this. They are saying this is matched under M, right? Some vertex Ui of Gi must be matched under M with the vertex Vi of S. That is what the sentence. So here what they mean by this sentence is, here you have, for this edge you are having vertices U1 and V1. So matched under M means this U1 and V1 will be present inside the matching M. Okay, that is what in sentence they are saying. Some vertex Ui of Gi, it is Ui is present in here, right? So some vertex vi of gi must be matched under M with the vertex vi of S. So from the figure you are writing, near to this you have to draw this figure. So after that, from the figure you are saying that since this v1, v2, etc. up to vn are the subset of S. Is that right? From the figure you can say that. Therefore, number of odd components of G minus S equal to n. Here, odd components of G minus is n, right? Because you have G1, G2, etc. till Gn graphs you have. These graphs having odd components. These graphs are odd components. So, how many graphs are there? N number of odd component graphs are there, so that you are writing number of odd components of G minus S equal to n, and this will be equal to, here also you have n number of vertices. So in this n is equal to, you can also write like this also, number of vertices. Modulus of this means what? Number of vertices. It means number of vertices, right? So here also when you put modulus and write all these, it means what? Here also you are having n number of vertices. So in the here you can write n equal to this. So this is less than or equal to mod S. How? Because this value is subset of S, therefore you can write this is less than or equal to S. From this you are writing this. Now from this line you can write number of odd component combining this and this, so that you will get number of odd components of G minus S will be less than or equal to modulus of S for all S subset of V. This is how you have proved the first part of this theorem. You have proved it, right? Now we can see the converse part in the next video.